Thank you so much, Johan. It's a real pleasure to be sharing the stage today with the most amazing co-author and collaborator I could have wished for. Jonas will be playing his part in just a second. My name's Marco, and we are really excited to share with you some of the Diophantine mathematics that we've been working on for almost a decade. So this is all the mathematics that relates to Hilbert's 10th problem, which we formalized a couple years back. And more importantly, though, we have a new mathematical result. I think it's the first time we're speaking about it at a conference. And it appears together with a formal verification. And so 4 years ago, this was in a very rough state. We knew we had some sort of result. It wasn't fully fledged out. And we decided, well, why not formalize the result? And that's what we refer to here in the title with its in situ formalization. We formalized the mathematics right where it happened. This is joint work with a lot of people. It wouldn't have been possible without any of them. So there are 2 senior mathematicians who gave us a lot of guidance on everything we did. There are 3 soon-to-be senior mathematicians who helped us with writing many of the proofs. And then there's a team of 14 students who worked with us in various semesters, various years, various countries, continents even. So most of them worked at ENS Paris. Some of them worked at University of Cambridge, and some of them worked at UC Berkeley. So we had a real international collaboration going on here. It's the culmination of 4 years of formalization work. And at least for Jonas, it's the culmination of almost a decade of work, which is kind of insane, where he started in his senior year in high school, or 12th grade in high school, working on some of these questions relating to Hilbert's 10th problem. Before we get started, I want to say that we're super grateful to the Département des Mathématiques et Applications, to the maths department of ENS, for sponsoring or supporting our little research group. We were just a bunch of master students at the time, but they gave us a little budget, and we had the chance to invite some speakers to help us learn Isabelle and learn a little bit about the research that's going on. Some of you are in the room, so thank you for coming back in the day. And we also organized annual retreats where we would formalize from like 9 a.m. to midnight, and a lot of this work was done. Okay, I kind of want to jump ahead, but let me lay some groundwork and talk a little bit about Hilbert's 10th problem and the underlying mathematics that you should know to appreciate our result. The problem. Hilbert in 1900 at the International Congress of Mathematicians asked, is there, in simple modern language, is there an algorithm to determine if a given Diophantine equation has a solution in the integers? What's a Diophantine equation? Some of you know. It's a polynomial equation over the integers with integer coefficients. And you're allowing multiple variables, so you're looking for solutions in some sort of lattice. And in general, that's a really hard question. Let's look at an example. Here's a Diophantine equation. It's 1 times a minus 1 times y squared equals 0. And more specifically, we like to think of these equations as parametric equations. So we have a parameter a, and we have unknowns y, x, y, z, w, and so on. Well, we say that this equation accepts the parameter a if there is a y such that we have a solution. So this Diophantine equation also equivalently encodes a Diophantine set, which is the set of all a for which there exists a solution. In this case, it's the set of squares. Right, great. So the set of squares is a Diophantine set, and throughout the talk, we'll be exchanging the notions of Diophantine equation and set kind of as we go along. Now, the solution took 70 years to be completed. And it was Yuri Maciasiewicz who succeeded in completing this proof that every recursively enumerable set is Diophantine. Because we know that there are some recursively enumerable sets that aren't decidable, refer to the halting problem, there cannot be an algorithm that can decide all Diophantine equations. However, there's many generalizations, as with many of the Hilbert problems, there's many generalizations of the problem that are still of interest to many researchers around the world. So one version you might say is, oh, this was actually the original phrasing of the problem. What about Hilbert 10 over the rational numbers? It's still an open problem. It involves some really fancy and really complicated mathematics. For us, we instead restricted the problem to subclasses of equations which have a bounded complexity. Now, don't get me wrong, the class of equations is still infinite, but we restrict the complexity of these equations. And we're looking for negative solutions of Hilbert's 10th problem, which means we also want an undecidability result. There's no algorithm that can decide and then a restricted class of equations. So the correct notion of complexability that we like to work with is something with the number of variables and the degree of the polynomial constraint. Which leads us to this central definition of our talk, which is that we have, let's see if this works. We have nu and delta, and we call this a universal pair if any Diophantine equation can be encoded in a polynomial, if any Diophantine set, can be encoded in a polynomial with at most nu variables and at most degree delta. Right, so again, this is an infinite class of equations, and it's actually highly non-trivial to show that such universal pairs exist, but it is possible. And as soon as you can represent all Diophantine sets in this class of complexity, we say that this is a universal pair, and this class of complexity is also undecidable. Let's try to build some intuition about all of what I just said. Pop quiz, slide number 3. Let's see who's still paying attention. Is the set of primes Diophantine? Why? Why? Bingo, yes, exactly. The primes are recursively enumerable. I'm sure many of you have written the program. And here is a polynomial that represents the primes. It has 26 variables. A through z all appear at least once in this polynomial. Right? Now, we can do more. Diophantine equations are really cool. So maybe some of you are familiar with the Collatz problem, the 3n plus 1 problem. You define this function on the natural numbers, which for even numbers just divides by 2. For odd numbers, multiplies by 3 and adds 1. Collatz conjecture is a famous open problem. It says that for every natural number, if you iterate this function, you will end up in the cycle 4, 2, 1, 4, 2, 1 ad infinitum. This seems like, oh, we have integers or natural numbers. We should be able to reason about them using Diophantine polynomials. And indeed, this is possible. I believe this was your high school project, right? To write down the polynomial that encodes the Collatz conjecture. This is a polynomial that when you plug in the number n as a parameter, it has a solution if and only if that number ends up in the cycle 4, 2, 1. That polynomial is 36 pages. We didn't print it out to save paper, but we have the PDF, which we can share with you. And so if you want to be tongue-in-cheek, you can rephrase the Collatz conjecture as, oh, that polynomial encodes exactly the Diophantine set of the natural numbers. It gets even cooler. The Goldbach conjecture, which states that every even number is the sum of 2 primes, can be encoded in a Diophantine polynomial. The ABC conjecture, a little bit more involved, also a number theoretic conjecture, can be encoded. And Yuri Maciejewicz, because of his fascination with the Riemann hypothesis, has spent a lot of time thinking about how to derive integral constraints about the zeros of the Riemann zeta function. And he's managed to find a Diophantine polynomial that has a solution if and only if there's a solution to the Riemann hypothesis. Pretty damn cool, right? Sadly, Diophantine equations are undecidable. Well, all of these open questions, which we can in principle encode with Diophantine equations, lead us to ask, oh, given an equation, can we find a simpler one? And this is exactly where our work comes in, because we have a result, and you'll see it momentarily, that given any Diophantine set, indeed there's such a thing called a universal pair, just as a reminder, the central definition of our talk, which states that any polynomial, if this pair is universal, can be represented in at most nu variables and with degree at most delta. At this point in the talk, I would like to point out the subscript of the natural numbers here and the new unknowns in the natural numbers, because it's important. We distinguish between 2 kinds of universal pairs. The first one are universal pairs over the natural numbers, where we allow unknowns in the natural numbers. And the second are universal pairs over the integers, where we allow the unknowns to be in the integers. Those 2 things are not the same, even though you'd think, oh, wait, those are so similar. Here's an example why that's different. Inequalities are Diophantine. So the set of all A which verify this inequality is a Diophantine set. How would you encode this over the natural numbers? The answer is there exists a y in the natural numbers such that A equals y plus 3. Now, this same trick doesn't work over the integers. Right? You do not get an if and only if correspondence between the 2 statements. What do you do instead? You use Lagrange's 4 squares theorem. So over the integers, you write there exists an x, y, z, and w, such that A is x squared plus y squared plus z squared plus w plus 3. So you can see that naively, if we have a relation that can be encoded in a Diophantine way over the natural numbers, you can translate that to a Diophantine relation over the integers, but you need 4 times as many variables and double the degree. So we have this naive translation where using this 4 squares theorem, for any universal pair over the natural numbers, you get what we call trivial universal pair over the integers. Okay, but you need 4 times the variables, 2 times the degree. So let me admit for a second, because it would take too long to review all the literature, that there are universal pairs over the natural numbers. This was known since the 80s. The best you can do in terms of the degree is 4. Kind of cool. Because any higher degree equation, you can split it up, introduce auxiliary variables. You only get quadratic equations. You take the square of all of them. You sum them all up. That models a conjunction. And so you can get 58 variables, degree 4 over the natural numbers. If you want to reduce the number of variables instead, the best you can do over the natural numbers, at least as far as we know, is 9. But the degree explodes to 10 to the 45. Okay. Now, if you take this and plug it into our simple formula, 9 variables over the integers would give you 36 variables. All right, so we claim that we can do a lot better. Stay tuned for the answer. I want to share one more fun fact about this universality, which is mind-boggling to me. If you use a Gödel encoding for your proofs, you can take any proof and just encode it by a natural number. Right? You assign each symbol some sort of prime number, and you take the correct exponents. This result of the 80s says that for any axiomatizable theory T and any proposition P, if P has a proof in T, then P has another proof consisting of 100 additions and multiplications of integers. Kind of crazy. In this case, what we're using is not a complexity of number of variables in degree, but the complexity of number of arithmetic operations that we need to compute the polynomial, which is another measure that we didn't work on, but I just thought I'd share. If you're curious or you struggle to believe it, come find us at lunch or at coffee later on. Okay, without further ado, here's the actual result. Take a universal pair over the natural numbers. We've already seen that a couple of those exist. Then instead of 36 variables, which previously was the best you could do with integers, we have a universal pair with only 11 variables. That's 2 more than you needed for the natural numbers. And we have an explicit formula for the degree of the universal pair, which is calculated as the degree of an explicit polynomial that we construct in our formalization. And the degree is given by this formula. If you now plug in some known pairs, and in particular, I think the 58-4 pair leads to a pretty good value of eta, you can get this 63-digit number for the degree. And as a corollary, we have this explicit universal pair over the integers. And we formalize that assuming that there exists a pair over the natural numbers, we get the pair over the integers. Okay, that's my cue to hand off to Jonas to tell you more about the proof and the formalization. He has a mic.
I have a microphone. Yeah, so before I talk a bit more about the structure of the proof, I thought I'd give a bit of a flavor at first by showing some excerpts of the construction that we make. So as you can see, we define lots of polynomials. So all of these quantities you can see above me are polynomials. And they're very nested. So a lot of them depend on the ones that have been previously defined. So this got very tangled up, and we were quite confused about our own maths. And we wondered, can Isabel help us? But before we get to talk more about the formalization, I'll first give a rough idea of how the proof looks like. So in the theorem that Marco just presented, we can assume that there exists a universal pair for the natural numbers, and we then need to show a large equivalence. So we take a Diophantine set A, and we need to show that membership in this set A is equivalent to the condition which you can see down here, which just means that there is a polynomial which describes the set A in a Diophantine way, such that this polynomial has 11 integer unknowns, and the degree is bounded by the formula which we saw earlier. And then the way the proof proceeds is that we first make use of our Diophantine universal pair in the natural numbers to get the first line. So we then have a concrete polynomial, and this already has a bounded degree, but it uses natural number unknowns. And then there are various techniques in this theory of Diophantine equations which you can use to consolidate all of the unknowns into a single large number. And this takes fairly complicated Diophantine relations, but across multiple intermediate representations, one finally arrives at this polynomial P. Now, this is a lot of work, so we thought, let's not all do it ourselves. And fortunately, we found lots of amazing students who wanted to be part of this. So as Marco mentioned before, there was the work group at the ENS in Paris. Every year, we started with an Isabelle workshop to get people excited. The students who were working on this project all had no prior Isabelle or formalization experience. So we always had to spend about one semester on teaching Isabelle, hoping that the students would pick up enough to be able to contribute to the actual formalization later. To structure this work into multiple pieces that individual people could work on was actually quite challenging. Because when we started, we didn't have a nice written up draft of our mathematics. We, at some points, didn't even know really what the theorems should be. And there was a lot of movement of theorems being split apart into separate statements or lemmas being merged. But here you can see the structure that evolved eventually. The first line corresponds to the main intermediate representations, which I was talking about earlier. And this is then also how we split work across multiple students working on this. There was one very consistent challenge throughout this formalization project, which was how to work with polynomials in the best way. In Isabelle, in the AFP, there is a data type M-poly for representing multivariate polynomials. And you can see an example of how this might look like. So all the variables are indexed by natural numbers. And of course, this is not very intuitive. And if we have some complicated definitions like this, we probably want to stay on the more conceptual side and have a way to express this in Isabelle that's closer to our natural language mathematics. So we want to use Isabelle terms or Isabelle functions for most of the time, and then start using polynomials when we need to do actual degree computations. Fortunately, we had one of our students, Anna Danielkin, who developed a tool called polyextract. And this is a command in Isabelle which solves the problem we were having. Using this command, you can start with a normal definition. So here you can see this is the definition of B as defined on the left-hand side. And this is a simple Isabelle function from two integers to the integers. And then we run this command polyextract, and it gives us some output here. Namely, it creates a new constant in Isabelle, which corresponds to the multivariate polynomial. And it also includes a theorem which shows that this newly generated constant behaves as it should. This has to work with the deeply nested structure of polynomials that we have. So if, for example, you can see the polynomial m, which appears early on, is also used for t later. And we don't want to unfold all of these definitions into something that is very complicated and long, which we can't work with. So polyextract is also clever about dealing with this nested structure. And then finally, we have another command called polydegree, which we can use for calculating degrees explicitly. So we like to call this an in situ formalization because the formalization happened in the natural environment of the mathematics in a maths department. And really the manuscript in LaTeX and the code in Isabelle were developed at the same time. And it was great to see how both could influence each other across. There were some very concrete benefits to writing mathematics in this way. The first one is, of course, kind of trivial. We managed to fix a lot of bugs and iron out all the kinks that you'd usually get in your mathematical writing, annoying small mistakes. But then somewhat more substantially, Isabelle helped us to streamline our arguments. There were lots of cases when our lemmas had lots of hypotheses. So it was sometimes hard to see where exactly they got used and in which way they are actually needed for the proof. So in Isabelle, you can simply comment out some hypothesis, you see where the proof breaks. And actually, in some cases, this helped us to weaken the hypotheses or even get rid of one entirely. Another helpful aspect was that we had to be fully precise about our dependencies. There was one lemma which actually needed to cite a result from the literature that was not at all trivial. And this was only realized when we formalized it, and the formalization had to get a lot more complicated than we expected before. And then finally, what's nice about the formal proof is that you can experiment it a lot more. You know, when you change the definition of something, that Isabelle will check all affected parts, which you can't do as simply in your LaTeX manuscript. So for some parts of the things we were formalizing, I'd actually say that Isabelle worked as a proof assistant. There's one notable piece of mathematics where we had to establish lots of bounds, and the complexity lay mostly in sort of untangling the web of dependencies, and that's exactly what Isabelle helps you with. So that was more fun to do in Isabelle than on paper. Future work. I'll start with what other people might do. So one feature that we'd really wish for in Isabelle would be something like a blueprint tool that helps you to align natural language mathematical writing and the formalized proof in Isabelle. There's already a lot of infrastructure for this in Isabelle through the document generation framework, but I think that this could be extended, and there are some features we'd be looking for. And then crucially, to continue this work, I think really means continuing the mathematical research. There's still lots of open questions around variants of the undecidability of Hilbert's 10th problem. For example, there's little known for the number of unknowns between 2 and 10. And one can also consider universal pairs for multiple parameter sets, which has not been done yet. So to summarize, I'd say that our research unlocks a new method of researching Diophantine equations. We now have a lot of infrastructure in Isabelle that means that this type of mathematics can be done in novel ways, and we're excited to see how this will continue in the future. Thank you for your attention.